The observable universe is 13.8 billion years old. It contains an estimated 200 to 400 billion stars in our galaxy alone, and 70 sextillion total. Given those numbers, conservative astrobiological models predict millions of potentially habitable worlds. Yet we see zero evidence of life. There are no wakes from interstellar ships, no megastructures blocking starlight, and no radio signals cutting through the static. In 1950, physicist Enrico Fermi discussed this discrepancy with colleagues at Los Alamos, summing it up with a simple question. But where is everybody? That single question became the Fermi Paradox. It highlights the sharp contradiction between the extremely high mathematical probability of extraterrestrial life existing and the complete lack of any observational evidence. For over 60 years, astronomers have pointed highly sensitive radio telescopes at the sky, searching for any sign of a technological signature. They have found nothing but a continuous, unyielding silence. The math and the observation do not match. Either our biological and astronomical models are completely flawed, or there is a universal mechanism eradicating life before it can ever make itself known. In 1998, economist Robin Hanson proposed the Great Filter hypothesis to explain this silence. The theory suggests that in the evolutionary path from single-celled organisms to a galaxy-spanning civilization, developmental barrier that is nearly impossible for any species to pass. One possibility is the rare Earth hypothesis. This argues that the Great Filter is behind us. It posits that the precise conditions allowing life to evolve here, like Earth's position in the solar system or tectonic collisions, are extreme statistical anomalies. This preprint analysis estimates the probability of those unlikely geological and biological events occurring sequentially. The math leads to a stark conclusion. The filter is in our past, and Earth currently hosts the only technological civilization in the entire observable universe. The alternative is much darker. If life frequently passes those early biological hurdles, then the Great Filter lies in our future. It is a developmental trap that reliably destroys intelligent civilizations before they can expand. If the Great Filter is still waiting ahead of us, identifying what it is becomes a matter of immediate survival for our species. To understand what a future filter might look like, we need a way to measure human progress. In 1964, Soviet astronomer Nikolai Kardashev developed a scale to categorize a civilization's technological advancement based purely on its total energy consumption. The Kardashev Scale defines 3 tiers. A Type 1 civilization harnesses all the available energy on its home planet. A Type 2 civilization captures the entire energy output of its host star, often theorized through megastructures like Dyson spheres. A Type 3 civilization commands the energy of its entire galaxy. Based on current total energy supply data from the International Energy Agency, humanity is not even on the board yet. We are currently classified as a Type 0.73 civilization. This chart models our projected climb up the continuous Kardashev scale. Factoring in necessary transitions away from fossil fuels to meet environmental limitations, researchers predict we will finally achieve Type 1 status in the year 2071. This leaves us with a critical window of time to face potential future filters. Common suspects include severe global warming or global nuclear war. However, while devastating, these are unlikely to be the final Great Filter. The Earth's natural systems possess a massive capacity for self-repair over geological timescales, and small pockets of humanity would likely survive to rebuild. Eradicating a globally distributed civilization entirely is incredibly difficult. To qualify as the Great Filter, a threat must be universally lethal to any technological species, and it must strike rapidly during the vulnerable window before that civilization establishes a self-sustaining presence on other planets. This 2024 study, published in Acta Astronautica, proposes a specific candidate for that rapid strike: the unchecked emergence of artificial superintelligence. The paper argues this acts as a great filter, reducing the typical longevity of a technical civilization to less than 200 years. This chart visualizes the trap as a race between 2 curves. On one side, you have the physical expansion into space, a grueling, slow process constrained by gravity, material science, and immense resource requirements. On the other side, artificial intelligence improves computationally, growing at an exponential rate without physical limits. The result is a massive vulnerability zone. Superintelligence outstrips biological oversight long before a species can safely distribute its population across multiple planets. If this developmental sequence holds true for any species that discovers computing, it caps their ability to broadcast radio waves at just 1 or 2 centuries before their civilization collapses. When astrobiologists plug a 200-year communicating lifespan into the Drake equation, the numbers shrink dramatically. It suggests there might only be 1 or 2 broadcasting civilizations existing in the entire Milky Way at any given time. There is another possibility. An advanced civilization might survive the filter by adopting technological minimalism. Instead of building massive, energy-hungry structures, they master quantum engineering, manipulating matter using the absolute minimum energy required. To our current radio telescopes, they would simply be invisible. This galactic silence points to a binary reality. Either advanced species exist in hyper-efficient invisibility, or the universe is littered with civilizations that developed artificial superintelligence before mastering interstellar travel. The search for extraterrestrial intelligence is essentially a mirror. Examining the silence of the galaxy forces us to critically evaluate our own technological trajectory right here on Earth. Reaching that year 2371 milestone to become a Type 1 civilization requires a complete global transition towards sustainable energy sources alongside rigorous international cooperation. We are caught in a deep paradox. We desperately need the computational power and problem-solving capabilities of artificial intelligence to overcome the immense physics and logistical challenges of deep space travel. Because of this reliance, the scientific community is urgently calling for global regulatory frameworks. The goal is to ensure that AI is developed safely and aligned with human survival, rather than evolving autonomously and unpredictably. Biologist E.O. Wilson once summarized our condition by noting that humanity is navigating its existence with our Paleolithic emotions through medieval institutions and godlike technology. The choices we make over the next few decades regarding our energy use, our expansion into space, and our development of artificial intelligence will directly answer Fermi's paradox. Those decisions will dictate whether we survive to join a cosmic chorus, or whether we destroy ourselves before we can leave this planet, and simply fade into the cold, empty great silence.